Hello and welcome back to another video. Today we're just going to be covering the brief introduction to counting combinatorics. So like you may have heard of combinations and permutations, and that's a whole big section of mathematics and really a really important part of competition math, but it's a very big topic. So today we're just going to do a brief introduction into some counting and a little bit into permutations and combinations, and we'll go from there. So to start off, we're just going to talk about a problem to begin with. So if you have 3 shirts and you have 4 pants, the question is, how many different outfits can you make, where obviously an outfit is composed of 1 shirt and 1 pant? So what we want to do is we want to think about this problem first off is sort of as what we'd call a counting problem. It's a pretty simple counting problem, and it may seem simple at first, but the general concept is super important for sort of the foundation for combinatorics. So let's make sure that we completely understand it. Even if the problem is super simple and you know how to do it, it's really important that you understand sort of why that makes sense. So let's first think about this problem as let's choose one of our shirts. So let's say that we have a red shirt. Let's say that we have a blue shirt. And let's say that this is our green shirt. So let's just look at our red shirt. So then, if we're wearing a red shirt and we know we're wearing a red shirt, well, how many different pants can we wear with that red shirt? Well, the answer is 4 because we have 4 different pants. So I'm just going to draw these lines to represent pants. So those are our 4 pants. Now, if you look at the same thing, but for the blue shirt, you'll see, well, again, it's 4. So we'd have 4 different options. So if you continue this, you'd see, well, the total number of outfits would be what? 4 plus 4 plus 4. Because you see we have 4 here, 4 here, because those are our 4 total outfits. So really, it's just 4 times 3, which equals 12. So obviously this is a pretty simple example, but you'll see it's a really important sort of idea or concept that you'll continue to use throughout combinatorics, which is sort of this unit that you call in mathematics combinatorics. So let's try another example. So let's say that you have a phone number, and your phone number is, let's say your phone number is it's 10 digits. So you have usually 3, then 3, and then 4, right, at your end. So for instance, your phone number could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. That would be a pretty cool phone number to have. So how many different phone numbers do you think there are that you could possibly make? Well, we can actually use the sort of that same formula or rule we just did where we multiplied 3 times 4, because in each sort of, as I drew here, in each place, like sort of place value for in a phone number, there's 10 choices. You could have any digit from 0 to 9. So each place, you have 10 possibilities. And as we just showed, you multiply. So in that last example, when we had 3 shirts and 4 pants, you multiplied to find how many total combinations there were. So in this example, it would be 10 times 10 times 10. So that would be 10 to the 10th power. That would be the total number of phone numbers that are possible to exist. So that's sort of an introduction, quick introduction to counting. So now we're going to look at what we call combinations and permutations. So let's start off with permutations. They're a little bit more straightforward. So you may have heard the words combination and permutation somewhat already in math. And they're sort of, I would say, often sort of confused, but it's super important that you understand the difference between the two. So a combination is, and you may often hear this, but it's super important, is what people will say is when order doesn't matter. So that might not make much sense yet because we haven't really explained what a combination is. So let's look at an example of a combination. So let's think about the two different types of combinations. So there's two. There's repetition. So repetition is allowed. And there's when there's no repetition. So to elaborate further, for example, let's say that you have coins in your pocket. Let's say that you have 3 nickels and you have 2 dimes. So you have a 5, a 5, a 5, and a 10. So as you can see, we have repeats. We have 3 5s and we have 2 10s. So a combination of this combination of coins, for example, would be if you were going to choose 3 from this pile of 5 coins, you could have 10 and a 5. So that's, see, repetition is allowed. Then an example of no repetition would be pretty simple. You have no repetition. So if you're doing like lottery numbers and you have a bunch of lottery numbers, there's not going to be a repetition of a lottery number because only one can win. So in the combination, there's not going to be any repeats. So it's just important that you know that that's sort of the two types of combinations. So, for example, let's look at this lottery number example. So, for instance, let's say that you have the lottery numbers. Let's just make up some numbers. Let's say 4, 17, 71, 89, and 93. So there's no repeats. We're going to do first combinations with no repeats because they're a little bit more simpler. So let's now say that a combination, we would say, would be some group, some set from these 5 numbers. So let's, for instance, say, let's look at combinations of 3. So how we would sort of verbalize that, how we would articulate that, we would say, how many ways can you choose 3 lottery numbers from this set of 5? How many ways can you choose 3 lottery numbers from this set of 5? And mathematically, we can write that sort of a bunch of ways. We can write that as C, which obviously stands for combinations, then N comma R. So N is the total number. So in this case, N equals 5. And R is how many. So we just said in our example, we're going to try and choose groups of 3. So we'd write it as 5, 3. Oh, C, 5, 3. And then you can also actually write it another way. You can write it as NCR. Again, so the N would be 5. C stands for combinations. And R is 3 because we chose 3. So then the formula, which is super important, is N factorial over R factorial times N minus R factorial. So a quick recap on factorials for some of you who may have forgotten. We say a factorial is the product of all the numbers from N. So N times N down, N minus 1 times N minus 2, times 1. So 4 factorial, as I started to write, is 4 times 3 times 2 times 1. So it equals 24. So that's our super important formula. So in our case, it would be 5 factorial, because n equals 5, over 3 factorial, over 5 minus 3 factorial. So that would be 5 times 4 times 3 times 2 times 1, over 3 times 2 times 1, times 2 times 1 for 2 factorial. And obviously you see we can do some pretty nifty canceling. That goes away. So we're left with 5 times 4 over 2, which does equal 10. So there's 10 ways. We can choose 10 different groups of 3. So looking back at our set of 5, an example of that might be 4, 17, 71. Another group might be 4, 71, 89. So there's 10 of those. You count them out, but this formula is super helpful, and it's super important that you remember it because it's probably the most important sort of formula from combinatorics that you'll use throughout math. Oh, and one more way that you can write it is big parentheses, and then at the top of the parentheses n, at the bottom r. So I have no room, but it would be written as 5, 3. Let's give myself some more room. So that's another way for you to write combinations. So remember, that was combinations without repetition. So those are sort of the more simple, but also maybe more common example of combination. So it was also important to notice, I didn't completely emphasize that, but you saw how the order didn't matter. It wasn't like we have, oops, that's not right. It wasn't like we had 4, 17, 71, and that was a completely different group from 4, 71, 17. These are the same group because order does not matter. So the order of these 3 numbers is irrelevant. They're all the same group, which is why we would call them a combination. If order did matter, these 2 groups that I just, or 2 sets of 3 from this big set of 5, so we chose a set of 3 and another set of 3, they would be separate. They would be 2 different groups because the order is different. But for combinations, order doesn't matter, as I drew right there. So now we're going to look at repetition. So combinations with repetition, which are a little bit sort of more confusing maybe. So for this example, we're going to look at ice cream flavors because who doesn't love ice cream? So let's say that you have 5 flavors of ice cream, and I'm just going to write the abbreviation, but you have banana for B, you have chocolate, lemon, not really sure why I chose lemon, strawberry, and vanilla. So you have 5 flavors. So the question now is, how many variations can you make if you were going to have 3 scoops? So I'll say it again. How many variations will you have if you can have 3 scoops among these 5 flavors? So to sort of draw that out, one example might be banana, chocolate, strawberry. We're going to choose 3 scoops, and we're going to choose them from these 5 flavors. And remember, it's combination, so order does not matter. So this, banana, strawberry, chocolate, these are the same thing. However, in this case, we could have 3 scoops of banana. If you really love banana ice cream, that does work here. We're going to say that does count as a variation. Or maybe you like chocolate, lemon, chocolate, which would, remember, is the same thing as chocolate, chocolate, lemon. So maybe you like 2 chocolates and 1 lemon scoop. So how many different variations do you think there are? And a hint, it's not the same formula as before. It's similar, but not the same. So actually, what it turns out being is that, as I'll sort of diagram, I'll diagram it like this, because it'll actually help us understand, oh, that's going to be too small. It'll help us understand it a little better, and we'll be able to use what we just learned to sort of figure out this answer. So let me repeat the flavors. So these are the boxes of ice cream. So, you know, when you go to the store and you have those big boxes and they scoop it out of them from each box is a different flavor. So these are the boxes. So we have banana, chocolate, lemon, strawberry, and vanilla. So let's think about this like we are a robot, basically. So for instance, we're going to start here with banana. Let's say that we're going to get chocolate, chocolate, chocolate. How we're going to write that is we're going to start at banana, but we don't want banana. So we're going to move to the right. An arrow indicates we moved. We want chocolate, and we want 3 of them. So a circle indicates we got a scoop. We want 3. We now move to lemon, but we don't want it. We now move to strawberry. We don't want it. Another arrow. We now move to vanilla. We don't want it, so we draw that arrow. So that's how we can diagram what we just did. So this equals chocolate, chocolate, chocolate. So now let's try and do that example for, let's say we want banana, strawberry, vanilla. So how would we diagram that? Well, we know that we're going to start with banana. So that's a circle representing a scoop. We then move to chocolate. We don't want chocolate. We then move to lemon. We don't want lemon. We then move to strawberry. Oh, yes, please. I'll have some strawberry. We then move to vanilla. Oh, yes, please. I'll have some vanilla. So that's how we represent it. And what you'll notice, and this is the super tricky but super clever part, is in each variation, we always have 4 arrows and 3 circles because we always have 3 scoops. So what we can do now is we can rethink about this problem, and we can say, well, how many ways can we arrange the arrows and the circles? So what we'll notice is we have, like we said before, 4 arrows and 3 circles, always. So how can we rearrange them? Well, how many total positions do we have? Well, if we think about R, because remember our old formula involved N choosing R. So here, R represents the circles, because that's our scoops. We're choosing our scoops. So how many R's do we have? Well, we have 3, right? So R equals 3. And how many positions in total do we have if we let our N equal 5? Because we have 5 flavors. Remember, banana, chocolate, lemon, strawberry, vanilla. But it's not the exact same formula, because if you look at our arrows and our circles, we only have 7. We have 7 total positions, whereas usually we would have 5 without repetition. But with repetition, our numerator is going to be 7 factorial instead of 5. So I don't know if that makes complete sense. And the reason is it's because it's n minus 1 plus r. That's the total number of positions. See here how we have 7? Although n is 5, we have 7. And that's because of the repetition. So the formula for what goes on top is n minus 1 plus r factorial. So I'll write that for you guys. It's n minus 1 plus r factorial on the top. Because we're going to use the same formula where it was n factorial over n minus r factorial times r factorial. It's just that it's a little confusing because the n's and the r's in that old problem are different. So the n factorial of old, which was on the numerator, is really this value right here, n minus 1 plus r. Then, like we said, we had r factorial on the bottom still, and because r is still that, and we're choosing n minus r, we're choosing r factorial, which means that what's on top, n minus 1 plus r, minus r equals n minus 1. Because if you'll remember, the old formula was n factorial over r factorial times n minus r factorial. So our new n is really this quantity because we had 7 spaces. Even though n was 5, remember we had 7. So we realized our new equation is n minus 1 plus r. So that's what goes on top. R factorial is still on the bottom because we're still choosing 3 scoops. And then to find this quantity, it's still n minus r. It's just our new n, which is this, minus r, which is r is still the same, so it's n minus 1 factorial. So that's our new equation for combinations with repetition. So that's the very much more complicated side of combinations. So now let's quickly do permutations. So permutations are different from combinations in that order matters. Super important. Order of our combinations matters. They're still combinations, we would say, but we would say they're ordered combinations. And again, there's 2 types. There's repetition is allowed, and there's no repetition. So let's start off with repetition. Permutations are quite easier. So an example we already did. We already did a permutations example. We did the phone number thing, where we had the 10 possible places, and we had 10 possible digits, and order matters, because in your phone number, obviously the order matters. The order of the digits in which you arrange them is what makes it a unique phone number. And some of you may have noticed, the formula for that was actually n to the r. It was 10 to the 10, and the reason was because n represented the number of possibilities for the first choice. So remember that first digit had any possible value from 0 to 9. So we have 8, 2 more. So this digit right here has 10 possibilities. And that's what the n represents. We have 10 choices from 0 to 9. The r represents, well, we do it r times because we do it for the first place value, we do it for the second, we do it all the way until the 10th place value. So that's a pretty simple formula. It's just 10 for the first time, that's how many choices, times how many choices do we have for the second? 10. How many choices do we have for the third? 10. How many choices do we have for the fourth? 10, and so on. So that's just how we get our formula, 10 to the 10th. So permutations are pretty simple with repetition. So now let's look at the exact same example, but without repetition. So let's say you're making a phone number, but the digits can't repeat. So in that case, each digit is used once, right? Because you have 10 places and 10 digits. So let's write this out actually a little bit bigger. So you have 10 possible places. How many choices now do we have? Choices do we have for the first place? 10, right? Because we still can choose any digit from 0 to 9. Let's say that we choose 2. Remember, we had 10 choices. Now let's look at our second choice for our second place. How many choices do we have? Not 10, right? We actually have 9 because, remember, no repetition. So we can choose any digit but 2. So let's choose 7. So we had 9. How many choices do we have now? You might be catching on. We have 8. And so on. So actually what you'll see is factorial. So that equals a big 10 factorial. So permutations with no repetition are, there's n factorial of them. With repetition, n to the r. So permutations are definitely a little bit more simple, but that's going to be it for today's video. I know we kind of flew through permutations, but they are a little bit easier, like I said. But combinations definitely will take a little bit of time to sort of get used to. And this whole unit, this whole counting unit, this combinatorics, as we say, will take some time to getting used to. We'll definitely do more videos, I would assume, more lessons on this stuff, because there's so much to cover, and it's really brand new probably for some of you. So that was sort of a really fast introduction. I hope you sort of learned something. It was definitely fast, but it's hard to get all of it into a video that isn't 45 hours long. So I hope that you enjoyed it and you learned something. And as we always say, if you have any questions about anything, combinations, permutations, some random question on your math homework, feel free to email us, and we will get back to you. And hopefully we see you at the Zoom lesson, where we'll cover all of this topic and the problem set. And if you have any questions, you can come to that meeting, and we hope to see you there. So thanks for watching, and enjoy your week. Thank you.